We've seen before that we can implement recursive functions in curly even without adding a recursive binding construct. For example, if we want to implement Fibonacci, we can use this makerec function on a function that takes Fibonacci, and so on. And it all works out. Makerec is a variant of the Y Combinator here. Now, if we want to take this approach and do it in typed curly, then we have to fill in all the types. And as we try to fill into the types, we run into a problem right here. These dot dot dots, there's nothing that can go there that will make that work out. And the problem is that fx is applied to itself. That means that fx has to have a function type, but the argument type also has to be the same thing as the whole type of fx. And so we run into this infinite expansion, or if we try to infer the types, the occurs check will reject the program. So there's no way to use this encoding in typed curly. In fact, typed curly is very close to the simply typed lambda calculus. We just had some extra numbers and so on to get curly. And we can prove, we won't do it here, but we can prove that all programs in the simply typed lambda calculus terminate, which means it's actually not a Turing complete language. That result carries over to typed curly, and so we want to add something to typed curly to get that expressiveness back. And we do that, as we often do when things just fail to, when encodings fail to type check, we build them into the type system. So we're going to build into our language, typed curly, and its type system, a letrec form, as we have done before. So then we'll be able to write Fibonacci using letrec in the usual way. That means we are adding a letrec form to our grammar. In the grammar, we are naturally going to declare the type of each variable that we bind using letrec, but there are no changes to the type grammar, just to the expression grammar. And that means our expression grammar needs a letrec with a name, a type for the right-hand side, the right-hand side expression, and a body. And then in bindings, for the interp part, we will do the usual thing with a box of option of value. So we can start with none, and then as soon as we have a value, replace it with some. This letrec interp part is what we've seen before. So we start out, we create a box that initially has no value. That's so that we can create the environment and interp the right-hand side, which might refer back to that same binding that whose values we're getting. Once we get the value back, we update the box and then interp the body. So nothing new there. The new part is in the type checking part. And here's the type rule. It looks a lot like a rule we would write for let. It looks similar to the one for lambda. It says that when you have a letrec form of some variable x and you declare it to have type tal0, then that right-hand side needs to have type tal0. So that's what we see here. Make sure that e0 has type tal0, but in an environment where you're allowed to refer back to x. And if you do, x will have type tal0 as declared. Right? So we are assuming that x has the type tal0 while also checking that the value that comes back from this expression that it'll be consistent with that same type tal0. And then assuming so, then we can type check the body with that same variable's type binding, and we get back a type for the body, and that is the type for the letrec. If we turn this into code, it looks like this. When we type check a letrec form, we have the name that we're binding and its type, and we have two expressions, the right-hand side and the body. So we can type check those. We want to type check both of these in an environment where we can refer to n. And where interp had to do something complicated, at type checking time it's straightforward because the type has already been declared. It was the declared type right-hand side type there. So we just bind into that right-hand side type in our extended type environment, type check the right-hand side and body, and then we just need to make sure that the type of that right-hand side is in fact the type that we declared it to be. If it is, then we're happy and we return the type of the body, otherwise we complain about the right-hand side.